The equipment and materials generally weren't available. The stuff we bought for equipment was standard laboratory kinds of things. Laboratory furnaces, generally heated by glow bars. We had to get up to high temperatures, 1200, 1250 degrees centigrade in order to do the silicon processing we wanted. And not many furnaces were capable of operating those temperature ranges. But the standard laboratory equipment that you could buy didn't have flat temperature zones, for example. Typically, these were tube furnaces that were big enough to put a small piece of silicon in. Materials were a problem. In fact, one of Shockley's first major projects there was a new way of growing silicon that would avoid the contamination that generally came out of the crucible. That was a big project, although it never ended up quite being functional. Other equipment, we could buy standard bell jar evaporators, for example, which were useful for putting down thin films. But we had to build a lot of ourselves. I remember building a water system that involved several 5-gallon jars of water connected together so you could get distilled water to rinse the wafers with. It was building laboratory scale equipment from what you could buy out of the typical laboratory supply houses. That was one of my jobs in my education and subsequent work. I'd done a lot of technical glass blowing, making the old glass jungles that let you manipulate gases and purify materials. So I took the same technology and used it for the controls over the diffusion furnaces. Initially quite simple things, and then they became increasingly complicated as we figured more things we wanted to do. One of the furnaces that I tried to design after deciding we needed a long flat zone, I used platinum winding. I ordered a significant amount of platinum wire since the melting point of platinum was above where we had to be. I put double windings on the ends to compensate for the heat losses and actually got a fairly good flat zone in the furnace. Unfortunately, the furnace only lasted for about 2 weeks before the element burned out. It turns out that while platinum doesn't melt at these temperatures, somehow or other it's sublime. As we took the furnace apart, there were little crystals of platinum away from where the wire had been. And we had to send it off to a recovery company to salvage the several $1,000s worth of platinum that were in the furnace. I don't think we moved the state-of-the-art ahead very much. Looking back at it, it was really a dirty facility. It was hardly more than a Quonset hut, no air conditioning, no clean room capability at all. The net result was we had a very difficult time making devices with good electrical characteristics. We learned a lot of things not to do. And, when we went off and started Fairchild, we could use that knowledge of what not to do to start off in a new direction with a much better idea where we wanted to go eventually. Well, Fairchild got started again with the idea of making a double diffuse silicon transistor. And we thought we knew the direction we wanted to go. We divided up the various elements that had to be in place among the senior staff there, and each set out to do it. I took on diffusion and metallization, for example. Jay and Bob Noyce took on developing photolithography. I worked on some of the assembly technology. Sheldon Roberts worried about growing silicon crystals. Essentially, we divided up the job among the people who were used to doing the kind of equipment preparatory that were necessary. And we went out then to get the equipment we thought would be suitable for what we were tackling. We built furnaces that took advantage of an element that was available from Sweden that was capable of going to these high temperatures and not burning out in a couple of weeks. All of the equipment for the photolithography had to be developed from scratch. Photolithography had been used for printed circuit boards, but we wanted to really apply it to production silicon technology, and that required everything new. We had to develop the mask-making technology as well as the techniques for coating wafers with the photoresist material and so forth. So it was an extensive amount of new technology that we were bringing to bear on our first product. The machine we made for making masks was one that was developed internally initially using 3 lenses for 16 millimeter movie cameras, and it stepped 3 masks at a time for the 3 different patterns, and by having them all tied together, any error in one was repeated in the other, so the mask would actually align with one another.
Were there any special challenges in procuring materials for transistor production?
Getting pure enough chemicals was always a problem. We frankly didn't know how pure we had to get them, so we got the best available and pushed the suppliers to continue to improve the purity. The silicon itself, initially we thought we had to grow our own crystals, but I guess Knapik, who had been with us at Shockley, set up a company at that time to grow silicon crystals and supply them commercially. So while we made our own crystals in the very beginning, as soon as we could buy them on the outside, we'd abandon that particular part of the business. Yeah, Art Lash was my technician for a good part of the time there. He helped me build the furnaces, and then when we developed the gold ball bonding technology, where a small gold wire was put through a glass capillary that could be used to squish it onto make the contacts. We had a problem that the capillaries kept getting plugged, so we had to have a significant supply of these. Art became very good at making these things, so he was encouraged by our production people, Gene Kleiner in particular, who was in charge of that, essentially to moonlight and make glass capillaries on the outside and deliver them to us. Well, that business grew, and Art next upgraded the design of the furnaces we'd built at Fairchild and started supplying furnaces also from his company, Electroglass. And that was really the first company I know of that was specifically set up to deliver equipment to the semiconductor industry. And Art picked it up and improved it. And as so often is the case in the semiconductor industry, it wasn't long before the furnaces being supplied on the outside were better than the ones we were building internally.
So you started buying from Electroglass eventually?
Yes, so we did. Other people got into the furnace business also. But that's been repeated over and over again, that a company dedicated to supplying the equipment that has a broad market ends up doing a better job than an in-house equipment supply capability can. When we set up Intel, we decided we'd do nothing on equipment internally. We'd work with the vendors, and even if this resulted in technology we developed getting transferred to the rest of the industry, it would be the most effective way for us to continue to grow. At Intel, the challenge of the first fab was just getting it done in a hurry. We set I believe it was 4 goals that we had to accomplish before we could really make devices. And set up a wager between the people who had to do it and the people who were watching to see if it could be done. And these were pretty aggressive. It required getting these things done by the end of that first year. Now, we started really the beginning of August, and we wanted to get them done by the end of December. So it was really a challenge just to get it done. In fact, the last goal was actually achieved, I believe, on the 31st of December, with a little fudging in order to make that happen.
Do you remember the specific goals?
One of them was to make a stable MOS device, which requires getting everything purified and the like, and that was the last one that was accomplished. But it was accomplished by putting a barrier layer in rather than by cleaning things up so much that we could do it directly. But they involved the usual things about being able to make good junctions and so forth. They're relatively trivial, but things that took a time to set up. And the challenge of going from essentially an empty building to being able to accomplish these things in the span of August, September, October, November, December, just 5 months, was really a challenge. We gave each of the engineers a book of purchase orders, each of the engineers responsible for a particular area. Not requisitions that had to go through a purchasing department or anything, but the engineer would talk to the salesman for the equipment, handwrite the purchase order and hand it to them as soon as the equipment was specified, just to get everything going in a hurry. It shocked the salesmen quite often. They didn't know what to do with this kind of a purchasing procedure, but it was very effective in a startup. I'm sure that's the case. The WestCon show came at the right time of year for us to do that. It was here locally, as I recall, and we needed the equipment pretty badly. I think an evaporator came right off the floor. I don't remember what else, but I know rather than have the company ship the equipment back to their factories, if we could get it shipped to Intel at that time, it helped us get started in a hurry.
Now, so in building that first fab at Intel, you could get all the equipment off the shelf from outside. Was there anything you had to build?
I don't remember us really having to build everything. We had to adapt a few things. In particular, we had to adapt an epitaxial reactor to deposit polycrystalline silicon, trying to do the silicon gate MOS. But the only things we would build would be a few relatively simple jigs and fixtures. We just tried to work with the equipment industry.
Now you've talked about this a little bit before, but companies like IBM and TI built their own equipment, and they were holdouts. That they resisted buying from independent suppliers for a long time because they thought that was their competitive edge. But you were completely the opposite at Intel. What was your thinking in terms of just not wanting to have any proprietary in-house equipment?
The thinking about our approach at Intel resulted from some of the problems we got in at Fairchild. The typical situation being we would build a first generation of equipment that would work. What we learned would be picked up by the equipment vendors, and pretty soon the equipment available on the outside was better than the stuff we did internally. I mentioned earlier where this happened on diffusion furnaces. Probably the strongest example had to do with epitaxial reactors. Again, in the beginning, we had to build our own. There was no equipment industry to supply them. But we built a couple of kludges that worked after a fashion. But the commercial machines turned out to be a lot better than what we were doing internally. So it wasn't long before we had to abandon our internal efforts and adopt what was available on the outside. And we began to see this as a pattern, that you just couldn't maintain state-of-the-art equipment internally because you didn't have the customer base that needed something new all the time that lets you keep improving things. You kind of got locked into a generation for a long period of time. You would have to make a big improvement, which was a lot harder to do. So the equipment industry and the semiconductor processing industry really were very complementary, and increasingly, I think that split has been recognized by everybody. I was interested then at that time in doing some venture capital kind of things. Applied materials looked like an interesting possibility. I guess I never expected we'd end up being their biggest customer. In fact, when Intel started doing much with Applied Materials, I sold my investment in it. And it started to look more like a conflict of interest.
Okay. So your investment wasn't so much to support an equipment company, but just a VC type?
That's right. I was looking at it as a financial investment rather than something to help us get equipment later down the road. The equipment vendors had to match the schedules of the semiconductor suppliers. I remember giving a talk at the semi meeting once, trying to explain this problem generally, that the bus leaves on a particular set of technology at a particular time, and if they're not in that first bunch of equipment, they lose that whole generation. They can come in 6 months later with a better machine, but it wouldn't be used by Intel. The process had already been developed with the equipment that was there. So they had to have equipment ready to match our schedule of new technology, or they had to wait typically 3 years and get on the next load. And this was always a complicating feature because it was a change in the way the industry was operating. We wouldn't always buy a better mousetrap. It would only be on occasions that we could get one qualified for use in the next process. The silicon cycles?
Yeah, silicon cycles, the up and down.
The thing you learn in this industry fairly early is it tends to have cycles. We certainly did develop a strategy. The philosophy was you never get well in the old products. These cycles for the device suppliers were generally price-driven, not volume-driven. In fact, if you plot the volume of devices, you see very, very few dips and very mild ones. You plot the dollars and you see very wide fluctuations. Cases, I know one case, for example, it kind of etched in my mind, where Intel's most profitable product price fell 90% in 9 months. While the industry is good at decreasing costs, it can't follow that kind of a curve. So these cause fairly abrupt dislocations, but that price never comes back up. You only get the increased revenue by moving on to the next generation of products. So it's very important that you continue the R&D investment across the bottom of these cyclical recessions. You always have to have the new things coming out the other end. And this is something that tends to be counterintuitive to people used to operating in other industries, where you cut your costs, which means often cutting development and one thing or another during the recessionary periods, and build them up again during the others. Here you can't do that. You have to keep developing the new stuff. In fact, you even have to accelerate the development of the new stuff across these negative periods. There's an opportunity to work with them. The problem is that those are periods when you're typically not putting in new capacity, at least not in any quantity. You're developing new products, you're developing new technology. So the equipment supplier suffers even worse than the device manufacturer. Their order book often turns negative during that time as people start canceling orders faster than the new ones are coming in. It reflects the problems that the semiconductor device manufacturers have much more strongly than the equipment manufacturers. And it can even be worse than that on some of the material suppliers. If you look at something that includes the desire to decrease inventories during these periods, for example, the silicon suppliers may find they don't get any orders at all for a while. It's the nature of this kind of a industry where we each depend on somebody further back in the line. The poor guy at the end of the chain gets really whipped during these recessions. You try to do something to make it, at least so nobody dies during the period that the companies are there when you need them to come back. But it's pretty traumatic for everybody.
Now, did these cycles exist going back, like the Fairchild days, for example? It was the same thing?
These cycles have existed about as long as the industry has. I remember them in the early 60s. We weren't doing an awful lot of business back in the 50s, but they come, no two of them are exactly alike, but the one characteristic they seem to share is a price collapse. The original paper, which Moore's Law got its name, made a prediction for 10 years that the most complex integrated circuits would go from about 60 components to something like 60,000, a 1,000-fold increase in complexity. That was a wild extrapolation of very little data. I was just trying to get across the idea that integrated circuits were going to be the route to cheap electronics, something that was not clear at the time. And amazingly enough, that 10 doublings in complexity that I predicted turned out to be 9 doublings actually, pretty close, much closer than it had any basis to be, but it got the name Moore's Law, which has stuck to everything that changes exponentially ever since. The first prediction for 10 years was all I was willing to state. In 1975, I redid it, changed the slope, and again expected, a decade or so to be all we were looking at. And in fact, we've stayed on that amazingly closely ever since. In fact, if anything, we've done better than my revised prediction in 75. But someday all exponentials on physical quantities predict a disaster. And we're getting pretty close to molecular dimensions in the devices we're making now. And that's going to become a fundamental limit in how we can continue to shrink things. So it's going to change after another 2 or 3 process generations. I don't know exactly when. I was surprised. There was no reason really to believe quantitatively that was going to be that close. Now we're at the point where people in the industry recognize they have to move that fast or they fall behind. It's a funny industry. The next generation of technology gives you performance improvements, reliability improvements, and cost improvements simultaneously. If you fall behind the leading edge on the kind of products that need it, you fall behind on all fronts. So it's very important for participants to stay on that leading edge. The price performance improvements applied by the semiconductor industry have driven most of modern electronics. You can look at other places where you get the same kind of thing. For example, disk storage, which is nicely complementary to the semiconductor devices. But over a long period of time, it's hard to see any technology that has remotely given the same kind of cost reduction. The only one that I can point to perhaps is printing, where the first Gutenberg press kinds of letters must have cost the equivalent of a few dollars a character. And now you get the New York Times on Sunday with lots of characters for a few dollars. But the semiconductor industry has made bigger changes in a few decades than printing has over a few centuries. It's a marvelous technology where the characteristics are driven by the physics of the devices. The old statement that if the auto industry had improved at this rate, you'd be getting 1 million miles a gallon and so forth today. Somebody once pointed out to me from the audience, but yeah, the car would only be 2 inches long and ½ an inch high, and not very good for your morning commute.
Integrated circuit. Again, when I talked to Jay last, he recalled that most people at Fairchild at the time viewed the IC as a research curiosity. When did it become apparent to you that it was going to be something big?
Most people must address a different population than mine. I don't think we considered it a research curiosity. We considered it a product. And when we did the first integrated circuits and moved them on into engineering and production, I remember assembling a group in the laboratory and saying, okay, we've done integrated circuits, now what do we do next? We started looking at other physical phenomena and the like. But we still had work going on in integrated circuits. At that time, I don't think I had the vision to see how far this could go. But it was only a couple of years after that I published the Moore's Law paper. So we were beginning to appreciate that this could be really a major change in particularly the cost, but in the nature of electronics industry. The early ICs were expensive and could only go in applications where weight or volume was extremely important. These tend to be military, NASA, aerospace applications in general. So the early applications there didn't surprise me. Now, if you change the question to early applications of the microprocessor, then my answer is completely different. The first microprocessors after the calculators went to a variety of funny applications. The one that stands out in my memory was somebody automated a hen house, taking advantage of the fact here was a computer you could program to do the things you want. Now, I don't know what you do when you automate a hen house, but I remember that was a peculiar application. In fact, I remember board meeting, one of the board members asked, when we were looking at applications of the early microprocessor, when are you going to get a customer that I've heard of? The people buying these were startup companies, were obscure little operations. They weren't the Fortune 500 that I sell to today. No, the integrated circuits we designed at Fairchild initially were general purpose logic circuits we expected people to use to build computers and computer-like systems. Then we started doing linear circuits that were fairly broadly applicable. It was only when we got specifically into a major program like Minuteman II that the circuits were designed very specifically for a particular application. But that was one program. We were still doing the general purpose processors, general purpose circuits with most of our development capability.
Had there been a better theoretical understanding, could the technology have skipped over vacuum tubes completely and moved directly from the early solid-state research of the 1930s to transistors?
Sure. If vacuum tube hadn't been invented and the transistor had been, that would be a completely acceptable path for most of the things we want to do. There are still places where vacuum tubes do things that we can't do with solid state. These tend to be high power, some very high frequency applications. But otherwise, if electronics had grown up around the transistor rather than initially around the vacuum tube, it probably would have been simpler in a lot of respects. It's just that getting the first solid state device, it could be an amplifier, it took a lot longer than people expected. It took a lot more material science. The actual idea of an MOS transistor was patented in the mid-20s. You just couldn't make it practically at that time.